In this video, I will talk about how to solve 2023 AP Physics C Mechanics Free Response question number 2. Okay, so let's look at this question first. A student makes a torsional pendulum by suspending a uniform disk of mass m and radius r from a light wire with torsion constant kappa that is attached to the center of the disk as shown in the figure 1. So that's this figure here, only one disk. The rotational inertia of the disk is given by I equals 1/2 mr squared. The student conducts an investigation to determine the relationship between the period of oscillation capital T of the torsional pendulum and the number n of identical disks that are suspended from the wire. So here's in the second picture, it shows us the two disk situation. Okay, so now notice that the initial twisted angle theta naught are the same for both cases. The student starts with a single disk, holding the disk at a small initial angular displacement theta naught from the untwisted position. The student releases the disk from rest and the pendulum oscillates. The student records the period of oscillation for a single disk. An additional identical disk is attached as shown in figure 2, and the procedure is repeated for n equals 2 disks. This procedure is repeated through n equals 10 identical disks. Assume the disks move together as one system. Question A, using t equals 2 pi square root I over kappa, derive an expression for t as a function of n. Express your answer in terms of mr kappa n and physical quantity constants as appropriate. So the equation involved in the torsional pendulums is the following. So the center wire here will provide a torque. So when we twist this by some angle theta from the equilibrium position, so let's say here is the equilibrium position. And now we twist the disk by this angle. So that's theta angle. Okay. Now this wire, the center wire here, will generate a torque trying to go back the equilibrium position, and that torque is called restoring torque. So this one is similar to the simple spring system where we compress or stretch a spring. The spring will try to go back to its original position, original length, and that is called the restoring force. But now for rotation, we will say it's the restoring torque. Okay, so the torque here is proportional to kappa, proportional to theta by a constant called kappa. That's the kappa given in the question. And when we write down Newton's second law for rotation, the torque here is trying to reduce the angle theta here. So the direction here now is negative. Think about this case here. The displacement is counterclockwise. The angular displacement is counterclockwise. However, the torque is clockwise, so that's why it's negative. Equals I alpha. Okay, so I is the moment of inertia. That's the same I in the question here, and alpha is the angular acceleration, so it's the second derivative of angle theta with respect to time. Okay, so that gives us the differential equation from Newton's second law for rotation, and we will try to solve this differential equation using the standard form. standard differential equation. And in that case, we will write this equation as the following. So it's single out the second derivative, and then divide by each term by I. So we will have kappa over I theta equals 0. So that form is called a standard differential equation for rotation, simple harmonic rotation. And the solution here is theta equals theta naught cosine omega t plus some initial angle phi naught. And theta naught here is the same value as this angular displacement theta naught. Okay, so that will be, yeah, sorry about that. So that's the initial, that's the amplitude, which is the initial angle. And finally is the phase constant. You can also say initial phase. So that's when you start timing t equals 0, and then the angle will be phi naught. Okay. All right. So now let's see. The solution here has an omega. Right. Omega is called the angular frequency. Omega equals square root kappa over I. Okay. Okay, so omega is square root of kappa over I and equals 2 pi over t. Okay, so the period t is 2 pi over omega, 2 pi square root I over kappa. Okay, so that is also the expression given in the question. So now the important thing is that we need to substitute in the I here for n disks. For n disks, we should replace I with ni. Now, each I is 1/2 mr squared. Okay, so let's do that replacement. And then the period t will be 2 pi square root n mr squared over 2 kappa. Okay, so that's the question 1. Question A. Now question B. The potential energy stored in the torsional pendulum when the disk is displaced is U equals 1/2 kappa delta theta squared. On the following axis, sketch a graph of the maximum kinetic energy Kmax of the torsional pendulum as a function of n for n greater than or equal to 1. So now for this question, I would say because the initial twist angle theta naught are the same for any number of disk for any n. Okay, so the total, or the maximum kinetic energy of the torsional pendulum will be the same. So Kmax will be the same for any n. And according to energy conservation, 1/2 kappa theta naught squared. So that's the energy given according to this equation here, right? The maximum potential energy is when we replace delta theta by theta naught. That is the same for all the disks together. So that would be 1/2 n ni omega squared, okay, omega max squared, and that is called k max for n disks. Okay, so they're together, right? We have this total kinetic energy of the system, and this should be the same, right? So if you want to draw like as a function k max as function of n, they'll be the same. So k max versus the versus n here will be just a straight line. It's a flat line, okay? So that's for B. Now for question C, now we have some data from experiment T versus square root n. And we have this scattered point, and we need to draw a best fit line for the data. Okay. Now, according to this relation, right, T equals this quantity. Let me copy that first. NMR squared over 2 kappa. Yeah, I think that is the expression. Yeah. Okay, so now since I need to plot T versus square root n, so let me single out all the let me group all the coefficients together. So I'm going to get 2 pi square root mr squared over 2 kappa. That is like the coefficient or slope times square root n. Okay, so let me say k times square root n. Okay, so slope is k given by the whole thing here. And this relation is supposed to be a straight line going through the origin. So you would draw a line going through, trying to go through the origin like that, right? Okay, so how to draw a line, like how to fit this data? So it's called the least square fit. The method mathematically is called the least square fit, meaning that now suppose you have a relation like this, right? T equals k square root n, and that's the assumed relation expression, and you want to determine this k here. But how to do that, right? And you know this n exactly, such as n equals 1, right? You know it must be 1 here for square root n. And let's say n equals 2, right? So that'll be 1.4, so it's about here, this dot here. And n equals 3, 1.7, something like that, this point. So for square root n equals 4, then we get 2 here, exactly 2, etc. Right? So n square root n here, you can say there's no error, right? In doing the measurement, you know that exactly. So for each n, let's say I have n1, square root n1, square root n2, etc. I can calculate from this formula. I can calculate T1 equals k square root n1, k square root n2, etc. Right? So that's from your calculation. Now we need to compare it with this data, and we will try to minimize a summation here. Let's call this sum. So we have your data 1 for T1. So I'm going to get rid of this T1 here. I'm going to say k square root n1 is from calculation. So that's from theory. And from experiment, you have data, let's say T1. T2, etc. So I want to use T here to represent the data, the measurement. Okay, so you're going to do T1 minus the data you got here, let's say this number here, 0.2 something, minus K times square root n1. K is the quantity to be calculated later. Okay, so minus K square root n1, and I want to square that. Okay, and the reason for that is because sometimes kn1, kni, square root ni is greater than ti, and sometimes k square root ni is less than ti, and we want to minimize that distance, that difference. So that's why I want to square them. So it's always positive. The quantity here is always positive. So you're going to write out all these terms, all these data points, and then sum them together. And then later on, you want to minimize that. So you want to take a derivative of this sum here with respect to k, and then you set that to be 0. Okay, and it turns out that to be this kind of best solution to minimize the summation here is given by a line we call the best fit line. The property of such a line will be it will try to go through as many points as possible. So why is that? Because if kn1, k square root n1 is exactly t1, the data that you measured in the experiment, then this difference will be 0. And 0 squared will be 0. So that's nothing smaller than 0, right? Because square here will be either a positive number or 0. So 0 is the minimum value. So nothing is smaller than that. So the best solution would be for each term here to be 0. Then we will get the best solution, right? But that usually is not possible. So what we want to do is that first, you make sure you want to go through as many points as possible. Second is that if that is not possible, then you want to draw a line so that the distribution of these scattered points will be symmetric along the line. So you want to put a line at the center so that there's an equal number. Okay, so the second best thing you can do is that there are equal number of points on the two sides of the line. Okay, so above the line and also below the line, you should have uniform distribution of the points. And if you're interested, I have in my app, I gave that solution, so you can look at that solution there. Okay, and it turns out that the best will give us a slope. You can read it directly from the scattered point. So let me try to draw a curve, and then I will give that data. Okay, so that's the t-axis. That's the square root n. So you have a curve that looks like probably like this. So that's equal distribution, and give me a second, I'll try to find the answer in my app. The slope from the best fit curve would be 0.5 minus 0.25, and then divided by 1.9 minus 1. Okay, so I read the 2 points. 1 point will be somewhere here and somewhere there, and yeah, sorry, here, I think. And that will give us the slope, and the slope is given by this number here. Now the second question is about can we use this data here and also the best fit line to calculate the mass of a single disk? Okay, and we also given this R radius and the kappa, the torsional constant kappa. So now remember, K, the slope, right, is given by this expression. So now if I want to calculate the mass M, I can rearrange all these terms, and then the mass will be given by K squared. K again is the slope that we just calculated, times kappa divided by 2 pi squared R squared. Okay, let's plug in the numbers. .6 for kappa. The radius is 0.2 meters. It's 0.2. Yeah, let's confirm that. And the answer is 0.16 kilogram. Okay, so that's part 2 of the question C. Now, sub-question 3. The student finds that the value given by the manufacturer for the mass of disk is less than the value determined experimentally in part C. Determine a single source of experimental error that could result in the observed difference in the value of M. Okay, so since I already know that I think these are here, there couldn't be any error. It can be measured pretty accurately. And also the kappa here was given, right? So we would say probably the measurement here, they're quite accurate, and except the case from the fit, right? And you're gonna need like square root n and also the t here to fit this data that you need to collect. And n is known exactly, right? Because we know, like from the picture here, you know, like just 1 disk, 2 disk, 3 disk, 4 disk, etc. So the only source of error is just the t. T measurement. Okay, and one thing I can imagine that can cause this T error would be, of course, there are like personal issue, like each person will read differently the period T, and when you do the period T measurement, you want to like count 10 times, for example, and then 10 full period oscillation, and then you divide by 10, etc. And that could be an issue. For example, the oscillation becomes non-ideal, so you're going to lose some energy there, right? So each time when you measure the T, when you do 10 times measurement, like each time actually there's a tiny difference. And another source of error could introduce this T error is that the angle is twisted too large. So that the torque we said that earlier, kappa theta, not this relation maybe is not true anymore because it becomes nonlinear. So what we have here is like a linear relation, and it only applies to small angle. Okay, now if you twist it too large, then the wire, right, its behavior becomes nonlinear. So we cannot use this relation anymore. Okay, so the oscillation is not simple harmonic oscillation anymore. So I think if you can say that in the in your answer, then that would be good. I think that would be good enough. Okay, so that's question D. The student repeats the experiment, but now the discs have a density that varies as a function of the radius of the disc according to rho equals 0.3 r. Question 1. Will the slope of the best fit line for this new data be greater than, less than, or the same as the slope of the best fit line in part C? Question 1. Okay, so now we need to look at this slope and again, this expression again. Okay, so instead of using the 1/2 mr squared, I'm going to use the original. Let me write that down. So part D. So the period t is 2 pi square root. So now it will be I over kappa. Okay. Now this I here could have two different situations. The first one is uniform. Let's call it IU. It's uniform mass distribution. Okay, and I also call this non-uniform mass distribution. So that refers to the case rho equals 0.3 r, right, in this question, and previously rho is a constant, doesn't depend on r. Okay, so rho equals constant, that will give us the I here equals 1/2 mr squared. Okay, so that's the case for uniform mass. Now for non-uniform mass, we can see because of this relation, the density relation, so density rho is larger at larger r, right, at larger r. So when r increases, rho as a function of r increases. Okay, so when you do the integral to calculate the non-uniform moment of inertia, you would do the 2 pi r square dr and then multiply rho here, do that integral. So that refers to mass, and then you need to first sorry, so a bit mistake here. This one is 2 pi r dr, sorry. So 2 pi r dr would refers to, so if you look at the disk, right, that's capital R, and you are digging out a small ring that goes from R to R plus dr. Okay, now this shaded area, so shaded area, small area, mass will be 2 pi r dr, that refers to the area, and then multiply the rho here, the density, that will give us the dm, the infinitesimal mass of the ring, dm of ring. Okay, and then that's why I have this here, and then that we still need to multiply r squared, right? That's the contribution of this dm here to the total moment of inertia. And the integral here goes from 0 to r. Okay, but anyway, this one is understanding of how to calculate the non-uniform moment of inertia. But you can see that R increases, rho increases, meaning more mass at large R. So that will increase the moment of inertia, meaning the non-uniform mass distribution will have a larger moment of inertia than the uniform distribution. Now going back to our period. Sorry, this one is the I shouldn't write down period. I should write down the kappa. Sorry about that. So yeah, sorry, let me change this one. So T equals Ni, right? So the slope, what we're interested in is the slope. So the slope is 2 pi square root I over kappa. Okay, so now you can see the slope for non-uniform will be greater than slope for uniform mass distribution. So the answer is larger than. Now, second part of the question, when n equals 1, the maximum angular speed of the torsional pendulum with a uniform disk is found to be omega u, and when n equals 1, the maximum angular speed of the torsional pendulum with a non-uniform disk is omega non-u. Which of the following correctly compares omega u and omega non-u? Okay, non-uniform. So we know we should start with the same angle, right? So you won't say the potential energy at the beginning, the elastic potential energy at the beginning is the same for both of them. And at the equilibrium position, we should have the maximum omega, right? Maximum kinetic energy for the rotating disk. So that's why the omega happens right at the origin where there's no potential energy. So now if I think about, let's say, uniform here, I should have omega max uniform. And that equals non-uniform omega max non-uniform. Okay. Now since we already argued that the non-uniform I is greater, so in order for this equation to be true, we should have omega u max greater than omega non-uniform max. Okay, so we should have that relation. Okay, so I guess that's all for this question. Thank you for watching.